radiation. And this is coming from a neutrino that is moving faster than the speed of light. And so you go, wait a minute, come on now. I've heard that the speed of light is the fastest speed that anything can go. So how could this neutrino be breaking the light barrier and producing shock waves of light? And this is something that's measured, for example, at the Large Hadron Collider, where you've got particles moving at very high speeds with incredible energies. You get these ghostly particles called neutrinos. And there's probably 1 billion neutrinos for more than every other particle in the universe combined. So the number of neutrinos outnumbers all the other particles in the universe combined, we believe, by about a factor of 1 billion. And so there's a lot of these things that are going through our bodies every second, maybe millions of them. They never interact, or hardly ever. Once in a while they do, but not very often. They could go through a light year of lead on the average without interacting with another particle. Of course, that's problematic, because if you had a light year's worth of lead, calculations indicate that would form a black hole. But if you ignore that fact, these neutrinos aren't very interactive. However, they can travel through a plastic, and the plastic has a speed that's less than the speed of light. So light travels through the plastic at a speed that's slower than the speed of light, and the neutrino is almost at the speed of light. So when it travels through a transparent substance that has a speed that's less than the speed of the neutrino, it's possible to produce shock waves of light. And that's called Cherenkov radiation. And this is an actual picture of that happening. So that's it for that subject. Let's take a look now at light. Okay, now, with the electromagnetic spectrum, this is another kind of wave motion. This is coming right off of that handout. We still have frequency times wavelength equals the velocity of the wave, but it's not a wave that's traveling through a medium anymore. It's the speed at which the energy is transmitted through an electric and magnetic field. So this is a very abstract concept. When you start getting to some of the more basic elements of physics, you start talking about field theory. And so we're going to have to slowly develop on that. That it's not the space itself that's vibrating or anything within the space that's vibrating. It's, if you can imagine these electric field lines as being like long elastic lines of thread or something. And then you start shaking one of these by oscillating a charged particle. That's going to send off ripples through this field. And it turns out this field energy can travel, does travel, has to travel at the speed of light. And so we still have simple harmonic motion of a charged particle. And this is what produces the electromagnetic waves. So the abbreviations here, SHM, again, is simple harmonic motion. And E and M is just electromagnetic. So it turns out there's a mutual induction of electric and magnetic fields that produces a light wave. But it's not a vibration through a medium anymore. So it's not a mechanical wave. And it always travels at the speed of light. And so c then, the speed of light, is also the speed of all other forms of electromagnetic radiation. It's just called the speed of light because it was discovered first for the kind of radiation that we can see. But then it was discovered that it's also the speed of infrared, it's the speed of ultraviolet, it's the speed of X-ray, it's the speed of radio, speed of microwaves. All of these travel at that same speed. It's actually the speed of light might more effectively be called the speed of causality. Because if you could travel faster than the speed of light, you could send a message, say, into the past to make a bomb blow up here on Tuesday and blow me up before I ever did this lecture. So I could violate causality if I could send information or have particles travel faster than the speed of light. And we'll justify that if it's true and see why that's true. That with c being the speed of light, we can write that then as 3 times 10 to the 8 meters per second, or 186,282 miles per second. And so this is our speed limit. For any other kind of particle, it can only go this fast and no faster. And even going this fast is a problem. It can approach this speed. But never quite reach it. Okay, so if we have a period of motion of our charged particle, that's going to send these ripples off through space. And so we can say then the frequency times wavelength equals the speed of light. And so if we had a radio wave, that's typically on the order of maybe 10 kilohertz frequency. And of course, when I'm talking about a radio wave, I'm not talking about the sound that you're hearing on your radio. That's a transduced version of the radio wave that has been turned into sound. I'm talking here about the carrier frequency for the radio wave. And so that's traveling at the speed of light. So the wavelength of a radio wave, if f is equal to 10 kilohertz, it's going to be 3 times 10 to the 8 meters per second divided by 10 to the 4 hertz. That'll give us 3 times 10 to the 4 meters. So that would be what? 3 times 10 to the 3 would be 3,000. So it would be 30,000 meters. That'd be 30 kilometers. So that'd be about 18 miles. About 6 miles per kilometer. And there's 10 kilometers. So this would be 30 kilometers. 6, 12, 18, by 18. So a radio wave then can have a really long wavelength, super long. And as it turns out, the radio waves can travel through the center of the galaxy. Okay, so the center of the galaxy has lots of obstructions in the way. But we can get radio information, for example, from an extraterrestrial civilization that was sending that radio wave energy through the center of the galaxy. The galaxy is shaped something like this. And so if we had an ET over here and was sending very long radio waves, we could receive those radio waves, even though it's going right through the center of the galaxy and this huge galactic nucleus and the galactic black hole, just because the wavelength is so long, it can average out all of the obstacles that are in the way. And so that's why when scientists look for extraterrestrial life, for signs of it, using the SETI, Search for Extraterrestrial Intelligence, they look in radio frequencies, because we would assume that the energy would probably be too faint if it was coming from another galaxy. So it would need to be coming from our galaxy. But if it's coming from our galaxy, then the farthest you can see out here is only about 30 light years around our sun because of all of the haze. You know, it's like looking out on the Channel Islands on a foggy day. You can't see the light that's coming from the center of the galaxy are the X-rays, but you can still, with a radio telescope, pick up the radio waves. So very long wavelength then for radio. As you go to kilohertz, then that would be 1.8 miles. And then as you drop down, you get to radio waves that are maybe the length of this room, but still very long wavelengths. If we want to go to microwave, then we're talking about a frequency of about 10 to the 9. So that would be 3 times 10 to the 8 meters per second divided by 10 to the 9 hertz. So that would be about 0.3 meters, or about 30 centimeters. So that's the wavelength of microwaves. And so since that wavelength is so big, this is why you can have on your microwave oven a screen that has gap sizes on the order of maybe ½ centimeter. That shouldn't be a problem because the wavelength is so long, 30 centimeters in relationship to this grid size, that this acts like a mirror and reflects the infrared or microwave radiation back into the microwave oven. One thing that was kind of interesting that we tried out a while ago was, well, is this microwave then, in a microwave oven, is that like the same as the carrier frequency on your cell phone? And the answer is no, not quite. The cell phones have had to jack up the frequency a little bit so that they don't crowd each other out. So they had to go to higher frequencies. And so what we did is we put a cell phone in a microwave oven, and we didn't turn on the oven, but we tried to call it, and it answered. So we were able to send the high microwaves through the little grid here. Okay, and so it's at least a factor of 10 bigger. We were able to send enough of those shorter wavelengths that could fit through the grid in order to activate the phone. Okay, so it blocks the kind of microwave that's in your microwave oven, but a grid like that isn't going to block cell phone radiation. Then if we go to still higher frequencies, we might be now on the order of the size of molecules. Okay? And so if we're on the size of molecules, typically that's on the order of 10 to the minus 10 to 10 to the minus 11 meters. So that's associated then with infrared. So that's on the order then of 10 to the minus 9 to 10 to the minus 10 meters. And so now the wavelengths are comparable to the size of the atoms themselves. Okay, and so as it's like a wave, you're sitting and the swell distance of the wave is bigger than the length of your surfboard, you're going to start bobbing up and down. And so that's what happens here. If it were like this, then it would all cancel out. And so this is what happens with a big aircraft carrier or something or a cruise ship where the swell distance is short relationship to the size of the object, is it doesn't move because there's as many ups as downs. But here, this causes heat because the molecule then rides this electric field, and it's the electric field that accelerates the charged particles within the atom and causes it to move up and down. So this is heat radiation. And so here then we're looking at, well, 10 to the minus 9, maybe it's say 10 to the 13th power hertz. That would be a typical infrared radiation that would produce wavelengths that are on the order of the size of an atom. As we go up to still, and remember that all of these are just the same old electromagnetic wave, that just with a slightly different frequency. And so it's our senses that are determining what that these are fundamentally different from each other. That in reality, they're not really all that different at all. It's just different frequencies and wavelengths, but the same basic process going on. Okay, and so if we get up to visible light, then we're talking about a frequency that's somewhere on the order of 10 to the 14 hertz. So in other words, if we can take this charged particle and vibrate it up and down 100 trillion times a second, then we're getting close to the kind of wave energy that we can see. Okay? And so the lambda range for visible light is about 400 nanometers to 700 nanometers. So you'll be getting used to that kind of unit of length because that is typical for what we're dealing with visible light. Nanometer, by definition, is 10 to the minus 9 meters, a billionth of a meter. Okay, so this is the same thing as 4 times 10 to the minus 7 meters. This is the same thing as 7 times 10 to the minus 7 meters. 700 times 10 to the minus 9 is 7 times 10 to the minus 7. So these are the, and so this then would correspond to the shortest wavelength. So this would be like blue light or violet. And this would be red, around 700 nanometers. And so let's try this then with 600 nanometers. Let's find the frequency at lambda equals 600 nanometers. So this will give us an idea. It's somewhere around 10 to the 14 hertz. But we can figure it out exactly by just solving. Frequency is equal to the speed of light divided by the wavelength. So that's 3 times 10 to the 8 meters per second divided by 6 times 10 to the minus 7 meters per second. So that gives us 1/2 times 10 to the 15, or 5 times 10 to the 14 hertz. So this is a typical frequency then of visible light is on the order of maybe 4 to 7 times 10 to the 14 hertz. And so that's what we see. And when you look at how the brain is structured in such a way so that most of our sensory input comes from visual sensations. And there's a lot of evidence to support the idea that our development of the brain and the development of sight came together in such a way as so that one would reinforce the other and you could make more complex decisions because of more information you're getting about the environment. But the thing here is that this range of frequencies is only about 1/1 billionth of all of the electromagnetic radiation that's being produced. And so if you were to think in terms of all of the frequencies as being like a distance, say spanning from New York to, or let's say London to Los Angeles, the electromagnetic spectrum would be about the thickness of this piece of paper in relationship to the distance, 1/1 billionth of the total amount of electromagnetic radiation is what we're using to construct almost our entire reality out of, which is shows us that there's a lot more going on than what we can see and what we can perceive. Yeah.
C you said is the wave speed, which is also the speed of light. Okay, we'll just double check that.
Okay, so the question is, why are we seeing in this range of frequencies and not in all the other ones? Wouldn't it be nice if we could see in all the other frequencies too? Well, yeah, it'd be nice, but just think about how much difficulty we have in managing our lives as it is. Sensory overload. Can you imagine if you could see that radio wave coming in and that X-ray coming in and infrared? Oh my God, probably go crazy almost instantly just from sensory overload. And there's also another reason, another couple of good reasons why we see in the visible range. One is that that's the kind of light the sun gives out the most of. So when we look at the black body radiation curve for the sun, remember we talked about this in Physics 2A. Black body radiation curve is just at a certain temperature. In this case, the temperature is the surface temperature of the sun. The sun puts out, this is the intensity versus the wavelength, puts out something that looks like a black body radiation curve. And so the peak of this is infrared, this is ultraviolet, so everything in between is visible light. And so this is a natural consequence of the fact that we've adapted to pick up the kind of light that the sun puts out the most of. And so could we theoretically see at very low wavelengths? Well, this would correspond more to X-ray. And at very high wavelengths, this would correspond to radio. So this would be, UV infrared. This longer wavelengths correspond to lower energy. Okay, and so shorter wavelengths that are higher energy. So, or would it be nice if we could see wavelengths that are on the same order of size as the size of bacteria? That'd be great, because then you wouldn't have a 3-second rule anymore. You would just know whether your hands had too much bacteria on them. You could wash your hands. But the problem with this is that the sun isn't putting out enough of that light. That's one problem. The second problem is that your eyes would have to be about the size of trash can lids to pull in enough of that light to actually make to discern that your hands were covered with bacteria. And so that's a problem then if you get into a fight, you know. You have these big eyes, a huge amount of evolutionary energy going into making these huge eyes. They're going to be the first thing to go in a fight, right? So that'll be taken out of the gene pool. So we had to optimize, make the eyes small enough so that we can have these little protective shields around them, preserve that evolutionary energy, and then we just have to bite the bullet on the germs. You just, maybe they're there, maybe they're not. We won't be able to see it. Okay, that's one of the principal reasons why we've adapted to see in that range of frequencies, because that's what we're seeing. That's what the sun puts out the most of, is that kind of light. And then also, visible light travels through water. And so that's not the same for infrared and ultraviolet. Infrared doesn't make it very well through water. UV doesn't make it very well through water, but there's a little window of the electromagnetic spectrum that allows for visible light to travel through water. And most theories of evolution indicate that life with creatures that could see began in the oceans. So you'd be blind then if you didn't see in the visible part of the spectrum. So those are two very good reasons why we're so interested in this very narrow sliver of the electromagnetic spectrum. It's just because that has been the part that has allowed us to survive by being sensitive to those range of frequencies we were able to survive, and that's why we're here talking about this. Okay, so if we go to still higher frequencies, 10 to the 16 hertz, then the wavelength is less than 400 nanometers. And if that's the case, then we have what's called ionizing radiation. So anything above visible will ionize or remove electrons from atoms, making them more prone to chemical reactions like sunburn. Okay, so ultraviolet radiation, then you need sunscreen to protect yourself from that, because that part of the electromagnetic spectrum at these shorter frequencies here is going to start causing damage. And then it causes more and more and more damage as we get to lower and lower wavelengths. So finally we get to X-rays. When we're down to X-rays, then the wavelength is small enough to cause mutations in our DNA molecules. And when we finally get to gamma rays, these are the shortest wavelengths of all. These are typically produced by the most energetic reactions in the universe, like, for example, material falling in toward a galactic-sized black hole. And that would produce these incredibly powerful gamma rays. There's some evidence that supernova explosions and gamma rays from black holes at the center of galaxies may help to trigger lightning storms, because it actually creates an ionizing path for the radiation as it travels through the Earth's atmosphere. And they've actually correlated gamma ray bursts with increased lightning activity. So wouldn't it be interesting if a star that blew up 400 years ago would, radiation is just getting to the Earth today, and it's causing lightning to happen today from something that occurred 400 years ago, and it took that long for the radiation to get to us. Okay. Are there any questions about that overview of the electromagnetic spectrum? Let's now, later on, we'll talk about things like radiation pressure, how laser beams can lift things off the ground, and how light can produce a force on an object. But in order to do that, we need to go back to basics, develop the principles of electricity and magnetism. So we're not going to do that yet. What we're going to do here is just start out at the end of chapter 33. Talks about the electromagnetic spectrum, and then goes to reflection and refraction. So that's all that you need right now. And I've given that as a reading assignment too, so that you can follow along just by going on the homepage. So what we're interested in sometimes is just the path that's taken by the light. Okay, and so we can define a ray as being the path that's taken by that part of the light that starts at the source and ends up at a particular receiver point. So theoretically then, if we think in terms of this being a continuous number, or a continuous amount of energy that's being produced off in all directions, so you have all kinds of different ray paths. If you're looking from here, this would be the ray path. If you're looking from here, then this would be the ray path. If you're looking from here, then the part of the energy that goes from the source to the receiver would be that ray path. And so we see then that for a spherically symmetric source of light, like is the case with the sun, or with maybe a light bulb or something that is producing light from pretty much just a point, and it's allowed to go off in all directions. that the rays are moving off in a spherically symmetric fashion. And so this gives rise to an inverse square law of intensity. The intensity is proportional to 1 over the distance squared. So this is the same kind of inverse square law that we saw before for sound waves. And I also used light as an example. But we have an inverse square law for spherically symmetric sources. Like the sun. And so here then, there's actually some wave action happening. This is like the peak of a wave, the trough of a wave, then another peak. So you could still think in terms of the wavelength of this thing. And you could draw it like that. So you can draw your ray and also indicate that it has a wavelength. But oftentimes that's left out in these examples. Just for simplicity, so that we don't have too many things cluttering up our diagram. And so if you were to move farther away from a light source, let's say they have a light bulb there, and then I double my distance away, it's not 1/2 the brightness, it's 1/4 the brightness. If I go 3 times farther away from that light bulb, 1/9 of the brightness. 4 times farther away from that light bulb, 1/16 of the brightness. And similarly for the sun, when you're looking at the other planets, and we talked about this before, Jupiter, 5 times farther away from the sun than the Earth, only 1/25 of the wave energy is hitting Jupiter that's hitting the Earth. Okay, so that's the inverse square law. However, oftentimes, we're just looking at a narrow range of rays. Let's say that this is the sun, then this is the Earth over here. Then that means that the only rays that could possibly hit the Earth are going to be ones that are going pretty close to parallel. The difference in the angle there is so small it's barely measurable. And so as we start looking at smaller and smaller portions of the ray patterns, as we get farther and farther away, the rays become parallel. And they can also be made to go parallel by a lens, or they could be produced in a laser, which would automatically make parallel rays. So a lot of times we'll be looking at parallel rays from a distant object. And so here's an example then of what can happen when these parallel rays move into 2 different kinds of materials. In one case, the parallel rays can be bent to a point of focus. And so this is what we call a refracting lens. And that brings the light rays that are parallel to a point of focus. Here we have what's called a, and this is converging, because the parallel light rays come to a point of focus here. Whereas here, we've got a different kind of curvature, what we call a negative curvature to the lens, and that scatters the light rays out. So this is called a diverging lens. So parallel rays scatter, and if you were to look from this side with a big eyeball, what you'd see is an apparent source of the light. So this would be what we call a virtual focal point. So both of these examples then are associated with light rays bending. talk about why refraction works in a couple of minutes. But there's also another way that we can deflect rays. So let's just put this under the category of ways we can deflect rays. So this will be one. And this will be two, called reflection. So in reflection, we have a bouncing of the light rays off of a surface. So here we've got the incident ray, here's the reflected ray, and our rule for how that works is that the angle of incidence equals the angle of reflection. Now this surface might be a calm surface of the water where you're seeing your reflection, or it could be a mirror. That's a more common example of a reflected ray. But typically, when we have light entering what's called a transparent medium, which means light is let through, some of the light will bend. So this only happens in a transparent medium. And some of the rays will bounce. And so we need to try to understand why these things happen and what the rules are for what happens when they are either reflected or refracted. And so what I'm going to do here is go back to my handout, to the second page of it. And so let's look at reflection. Now Richard Feynman was able to show that light actually takes every path. So in other words, it doesn't just go along the path that we usually see, but it goes along this path, goes along that path, goes along this path, every other possible path from source to receiver, that only the ones that have what we call constructive interference of the, and this has to do with quantum mechanics too, are going to produce what we call the classical path, which is the path that we see here. But what we can do to define this classical path is use what's called the principle of least time. This is Fermat's principle. Turns out that in a more comprehensive look at this, it follows what's called the path of least action. That's a little beyond what we need to look at here. We can just think of this as being the minimum time ray path. And so it could maybe go along this path and go up, or maybe it could go along that path and go up, but those are going to take more time. So there's going to be one path that gets us from source to receiver along the line that we actually see for the rays that satisfies the principle of least time. So here, get rid of this 2. That should be in there. This should be time then is equal to distance, which is the square root of y2 squared plus x squared over the speed of light, plus the distance for it to go up this way, which is, if this total distance is L and this distance is x, then this distance will be L minus x. And then this distance here will be y2, or y1, I'm sorry. y1 to this point. This is y2 to that point. Okay, so this is L minus x squared plus y1 squared. This is y2 squared plus x squared. Without that 2 down below. Get rid of that 2 over c. Then we just, so there's a certain minimum travel time. So this is the travel time versus x. We can plot that up. We can take the derivative of it to find the minimum time right back. Okay, and so basically then this travel time curve, take the derivative of it with respect to x, we get this expression. And then we set that equal to 0, and so we end up with this expression. X divided by x squared plus y2, y1 squared. This is L, and then this is L minus x divided by L minus x squared plus y1 squared. And so those are just the signs of theta, because the sine of this theta is equal to L over this is equal to the opposite side, L over x divided by y1. And this side here is equal to x divided by the square root of x squared plus y2 squared. And so those are just the signs of those two angles, and so they have to be equal. And so therefore, the angles are equal. So this just satisfies Fermat's principle of least time, in which theta incident equals theta reflected. And so this is the law of reflection. Very simple. And the actual calculations aren't that bad, although a couple of ones and twos. You might want to fix it. And so that's it. It does follow all paths, but then this is the classical path that it reduces to. So, so if we were to look at a reflection in a mirror, what we would see is the source of the light coming in so that the angle of incidence equals the angle of reflection. Theta and theta. But then each one of these points is getting a little farther away, so then at this point where it hits, this angle of incidence equals that angle of reflection. And then when this one comes in, then this angle of incidence equals that angle of reflection. But because they were starting to spread out, the reflected light also spreads out a little bit. It's just taking a little jog here on its way to your eye. So then your eye extrapolates along those straight line paths to produce what we call a virtual image. And so this is where the light seems to be coming from, but it's not really coming from there. And so reflected light produces not a real image because the light is still spreading apart, but it produces a virtual image. Where a virtual image is just a light trick. It's where the light seems to be coming from, but not where it's really coming from. But there's no source of light there. No real source of light. It just looks like it's coming from there. So your brain is being fooled, being tricked. Okay? But that's what produces the image you see of yourself, say, in the mirror. And it's going to be an equal distance on the other side of the mirror. If you do the geometry there, you see that those distances are all going to be the same. So when you look at a reflected object in a mirror, it looks like it's that much farther away on the other side of the mirror, and then reverse in terms of right and left becomes left and right. Just a couple more things on this, and then we'll go into our class activity. Here's the black body radiation curve, intensity versus wavelength for light that's coming from the sun. So we can see how it's peaked out in kind of the yellow part of the spectrum. Actually, it would look a little greener from space, but some of the green light is taken out by the Earth's atmosphere. And so it looks yellow to our eyes. They were able to measure the speed of light by sending, originally, light through a toothed wheel, and then in the amount of time that it took for the wheel to go through one tooth, they adjusted the omega of this thing so that this could go to a distant mountain and then come back again and then just go through the next tooth. And so from things like that, and also from a very interesting rotating mirror kind of a lab that we have here at Cuesta that we do in Physics 208C, you can get accurate estimates for the speed of light. But it's incredibly fast. It's almost 1,000,000 times faster than the speed of sound. So it could go around the Earth, the light beam could go around the Earth almost 7 times in 1 second. So there are the rays. And so here we can see then that when we're measuring the angles, in this case of incidence and reflection, we always want to measure with respect to a common reference position, which is the normal. So you always measure, you always construct a perpendicular to the surface first, and then you measure your angles from the normal. You say, well, why don't we just measure our angle from the surface? Well, then you're going to have a problem with, well, which angle? Is it this angle or is it that one? So there's kind of a non-uniqueness and a confusing aspect. But if you do it with the normal, then you don't have any of those problems. Okay, and so here, this would come in at 65, go out at 65, but then it would come in with respect to this inclined surface at 55 and go out at 55. Now this is what we call specular versus diffuse reflection. With specular reflection, this is like off a mirror, you can expect to see a very well-defined source of light here reproduced in the reflection. But in diffuse reflection, then the light can get scattered off at all kinds of different angles. And so that could be like a wavy surface where you don't see your reflection so well anymore. Or diffuse reflection could also be associated, say, with certain light that you might see from a really rough surface, which is no longer transparent. Here, we see an example of both refraction and reflection happening in the same problem. Still not showing it very well.
It is, you can see.
Can you see it?
Yes.
Hard for me to see it here. Oh, there it is. Okay. You see right along there. Here it's a little easier to see. So every time the light comes into a transparent surface, sometime you're going to get some of the light refracted and some of the light reflected. Now there are some exceptions to that, like what's called total internal reflection. But this is a general rule that any time that you have a change in the property of the medium, some of the light energy will bend as it travels into the medium and some will reflect off. So what about the refracted light? Why is it bending? Well, we can imagine that there is in a more dense medium, there's a slower average velocity. That's essentially what's happening. So when we go into a more dense medium, the velocity decreases for the light. And so the index of refraction then defines the speed of light in a vacuum to the speed of light in the medium, equal to c over v, where v is the velocity in the medium, and c is the velocity of light in a vacuum. And because the velocity is less, since v is less than c, n is always greater, less than or equal to c, n is always greater than or equal to 1. So this is what we call our index of refraction for the medium. And so if we want to follow that path of least time with a medium that has a slower velocity, we can do that down here, refraction. So I've gone through the details here. The light comes in, this is medium 1, then it bends when it's traveling through here. And what we end up getting here is that this is the sine of theta incident times 1 over v1. This is the sine of theta refracted times 1 over v2. So I'll let you ponder that. I'm not going to make you derive that. But this is equivalent to saying sine theta incident times n1 equals sine of theta refracted times n2. Because n2 is equal to c over v, so we could just go through and multiply both sides of this equation by c. So we take the derivative of the travel time, set it equal to 0, but with the velocity lower in this medium than in that medium. And we end up getting what's called Snell's law. So we can say, well, okay, I minimized the path of now it's not the path of minimum distance, it's the path of minimum time. If you were, let's say, a lifeguard here, and this were a drowning victim, you go, oh, I'm going to get to that victim as quickly as possible, so I'm going to go along the path of minimum distance. But that's not going to be the best way to save their life, because you can run faster through sand than you can swim through water. So there's a certain optimal bending angle that you would want to take so that you could save that drowning victim. Say, this is the water here, and this is the sand, this is the lifeguard, this is your drowning victim. There's a certain optimum angle that would get you there the fastest. Okay? And so another way of thinking of this is imagine you had a car that had wheels, and then all of a sudden this part of the car comes into the slower medium faster. Then that means that it's like slamming on the brakes on one side, but the other side is still moving faster. So that's another way to visualize what's causing the bending, is that this part of the wave comes in first, starts going slower. That gives the other part of the wave a chance to rotate. Yeah.
Do we know why light is making that calculation, or how it?
I go over it here. There are some misconceptions about that. You say, well, it takes longer for a higher frequency light beam to absorb and then be re-radiated by the atom. So that lowers the average speed. And you'll hear that in a lot of physics classes, but that's wrong. The correct answer I've got here on page 4, I think, here. So if you want to read through this, you can. What actually happens is that the electromagnetic wave causes the atoms in the medium to produce another wave, which is traveling in the opposite direction. Those two waves add together and create what's called a phonon. And that phonon, if you do the math, has a mass. And massive particles always move slower than the speed of light. So, but it's a little trickier than just saying that a higher energy light beam is absorbed and then re-radiated, and that takes more time, and so that's why it's going slower. And that's oftentimes what you hear for the explanation, but that's wrong. It's a little more complicated than that. Any other questions? Okay, so this is our Snell's law then. So we'll work with this in a lot of detail on Tuesday. And you might want to try to get started with a few of the homework problems. And I've also given you this challenge problem, which you can look at. Now this may make a little more sense to you after we've gone through in a little more detail some of these examples on Tuesday. But if you want to try to work on any of this stuff sooner than that, feel free. What I'd like to do for the rest of class today is go back to some of the stuff that we were looking at in chapter 17, and here's our group quiz. And so, see what you can do with this. I'll be in the lab today at 3:30, so if you have any questions with this, you can come by then, or if you have any questions with your simulations that you'd like me to try to work through with you, feel free. But here, this is something very typical to what you might see on the next quiz or midterm. Here we have a standing wave. It's in a certain harmonic. You need to find out all the things about the standing wave. On the back side, we've got busy traffic produces 80 dB with 100 cars, and we want to figure out the dBs if only 5 cars are moving per minute. And then for this one, you've got a carousel that is rotating round and round, and so it's producing waves that are Doppler shifted depending on whether the source in the carousel is moving towards you or away from you. And so show your work and select the right answer for that. We have 2 embedded tutors now. I'm very happy to have both of you. And if you have a chance to write your hours up on the board today, then are your hours established now?
Yes, they are.
Okay, good. So go ahead and put those hours up, and I'll write those down too. And then they're available to help you with these problems. Yes?